everyone. Welcome back to LAC for the 1:30 talk. First, a word from our sponsors. For LAC, it's OpenSUSE. OpenSUSE is proud to sponsor SCaLE, and the presenter you will hear from today, user OpenQA for a fully automated testing framework. And for big data, one-click install with OpenSUSE Factory. OpenStack, R, Ceph, Redis, IPython, and more are all available with OpenSUSE. Hack with us and build big data around OpenSUSE, which is based on the same technologies that SUSE uses. Our speaker is Weil, presenting storage tiering and erasure coding in Ceph. And if you look on the back of your badges, we have a link to a speaker survey. Please share your opinions with us when you have a chance. Thanks.
Thank you. Yay. It's funny that OpenSUSE is the sponsor, since they just announced a Ceph product, I think like 2 days ago. It's kind of exciting. So anyway, my name is Sage. I'm going to talk about Ceph, and specifically the erasure coding and tiering features present. So just a very high-level overview. I'm going to spend a little bit of time talking about some Ceph background, what sort of the system encompasses and how it's put together. I'll talk about Rados, which is the low-level object layer that it's all built on, and then cache tiering, erasure coding, and then give you a bit of a status update. Just a show of hands, I guess. How many people are familiar with Ceph? How many people run Ceph clusters? How many run Ceph clusters in production? Yeah, okay. So feel free to interrupt me at any time and ask questions. Things tend to be more interesting when that happens. So I'll talk just a little bit about the architecture, how the whole system is put together. But I'll start with a few motivating principles, why we built the system the way we did. So the first requirement is that all components in the system need to scale horizontally. There can be no single point of failure. Large systems are built out of a lot of pieces, and inevitably some of them are going to fail. We want to build something that's hardware agnostic, so you can buy parts from any commodity vendor, any kind of service that you want. Commodity hardware, hard drives, SSDs, x86 or ARM servers. We want to make the system self-managing whenever possible, particularly when systems get very big. We want it to be able to sort of make sure it stays healthy and holds itself together. And we want to build something that's 100% open source, that's free to use by anyone for any purpose. And sort of as a footnote here, one of the other things that we really tried to do with Ceph is to sort of move beyond the legacy architectures. We want to move beyond sort of this view of a big server and a client and talking to one server, and into a world where your storage system actually is a huge lake, a huge cluster, essentially, and the client is aware that it's talking to lots of different servers, and that responsibility for data is moving around, and build new protocols that sort of take advantage of that. So this is sort of a high-level Ceph architecture diagram that you may or may not have seen. So that the basic takeaway here is that the entire system is built on something called Rados, which is the red box here at the bottom. This is the part of the system that manages, racks and racks of different servers. It makes sure that data is distributed across those servers. It's separated into different racks. When things fail, it moves them around. When you add new racks, it migrates data. All of that is sort of handled by this low-level layer that we build other services on top of. And there's essentially 3 different APIs that we build on top of that currently. So one of them is provided by Rados Gateway. It gives you an object storage interface that's compatible with Amazon S3 or OpenStack Swift. So this is a RESTful API with buckets and ACLs and all that stuff. There's a block layer that's called RBD, the Rados block device, that presents you sort of a virtual disk that is actually stored and replicated across this reliable fault-tolerant cluster. And that's used for virtualization and general purpose storage. And then finally, there's a distributed file system called CephFS that gives you shared POSIX, distributed file system semantics, sort of like what you get with NFS, but instead of having a single server, you have a zillion servers that are all smart and magic. The sort of the underlying theme here is that we have lots of interesting services that we build on top of this core Rados infrastructure. I'm going to talk about a few of them in detail. So again, Rados Gateway gives you this S3 compatible object storage API. The way that this is typically deployed is that you have a number of gateways that are sort of presenting an HTTP endpoint to the rest of the world. Maybe you have a load balancer sitting in front. Maybe you use round robin DNS. Maybe you just have one, whatever it is. But it's sort of taking this high-level HTTP endpoint, and it's in turn storing all that data on the back-end Rados storage cluster using our native efficient APIs on the backside. You can also do sort of federated clusters with Rados Gateway. So this is sort of what you get out of imagine the same sort of thing that you get with Amazon S3, where you have sort of a global user and bucket namespace, but buckets might be stored in different data centers, and the system sort of has all the bits to do dynamic DNS and sort of redirect you to the right data center and all that stuff. It's all sort of part of the total solution. In addition to that, our multi-object story also does replication, so you can have everything on this data center replicated to another data center, so you can do disaster recovery. But the main thing that the gateway does is it makes sort of the low-level Rados protocol, which is we call object, but is not really what you usually think of when you say object, into something that is suitable for the web. So it's HTTP, you have ACLs and buckets and um, all the sort of standard protocols and so forth. It also has all the pieces to do billing and usage scraping and all that stuff, so you can build a full-on service that is sort of equivalent or competitive, perhaps, with Amazon S3 out of Ceph. The next piece is the Rados block device. That, again, gives you this virtual block device, virtual disk, sort of like a LUN, what you get from a SAN. And usually what people do with this is they use it for their cloud infrastructure. They're storing the virtual disks for their virtual machines. So most commonly, that means that we link in the librd client into the KVM hypervisor directly. So your KVM process that's running somewhere is just sort of presenting the VM with this virtual disk, but it's off-stored in the cluster. There's no special kernel support needed. But you could also use the kernel too. So mainline Linux kernel for many years now has had native support for the Rados block device. So you can map a dev RBD0 on a standard Linux host, the modern kernel, and that's actually backed by the storage cluster and is reliable and can be reattached to another system on another host. And it gives you a couple things. It takes a big virtual disk and it breaks it into smaller chunks and stripes them across the entire cluster, so you don't have sort of a busy disk bottlenecking on one server. You get read-only snapshots on a per-image basis. You have copy-on-write clones. You can have a master image that you efficiently clone for each virtual machine that you boot up. It's broadly integrated into QEMU, KVM, Linux kernel. There's iSCSI gateways with varying degrees of maturity, and it's well integrated in OpenStack and CloudStack and Nebula and Ganeti and all these sort of cloud frameworks, particularly OpenStack. That's where Ceph RBD is currently the most commonly used storage backend for OpenStack clusters. And there are some other things too, like incremental backups, so you can sort of have a disaster story deployed to another data center. And finally, the Ceph file system gives you, again, sort of a POSIX file system view. There's a whole new class of servers called metadata servers that manage all the POSIX file name stuff and load balance it and so forth. But then when you read and write file data, it goes straight to Rados, straight to the server that actually is storing your data. So they manage the hierarchy, they do snapshots and all that complex stuff. And it's a dynamic cluster, so you can have one metadata server, you can have 100, you can have one active, 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 passive, all that good stuff. But it's only needed for that shared file system if you use it. But all of this, again, is built on Rados. So I'm going to talk a little bit about Rados and how it works to give you some perspective, and then I'll talk about how the erasure coding and cache tiering fit into that. So Rados provides sort of this lower level local interface to store objects. Each objects are logically grouped into pools. It's sort of a flat namespace. Objects can store bytes like a file. You can put attributes on them. You can also store key value data, although we won't really get into that here. But it's essentially a very rich API to store data in the cluster, and the cluster handles all the fault tolerance and load balancing, all that stuff for you. It's a strongly consistent system because we're building file systems and block devices on top, so it's very important that we're strong and consistent. So this is very different from something like Swift or S3 where it's sort of eventually consistent and loose in that sense. We use Crush for dynamic placing. We're aware of the cluster topology, all good stuff. And from an application that's using librados, talking to the cluster, it can view sort of the cluster as a black box. Like you have a very simple API that says store this object, and the client library figures out where it goes, and you really don't worry about that. And the cluster on the back end is doing all the smarts to make it work properly. There's sort of two pieces in all that. There are the OSDs, which is sort of the individual disk, essentially, that's storing a bunch of data. And you have tens, hundreds, thousands of these in a cluster. And they're not just serving up data, but they're also smart. They talk directly to each other and do things like migrate data around on the backside. And then you have monitors that are the central sort of coordinators that make sure that everybody's on the same page and doing the right things that they need to do. You have a small number, maybe 3 or 5 of these in a cluster, just making sure that everything is sane. They handle like authentication, that sort of thing. But they're not part of the data path. Typically, in a deployment, you have a rack full of OSDs. In reality, you have hosts, usually a bunch of disks in those hosts. Each of those local disks has a file system on top, like XFS or ButterFS, and then there's an OSD process on each of those disks. So if you have a 32-disk server, you're going to have 32 OSDs on that device, on that host usually, that are all part of the Ceph cluster. That's typically how it works. One of the key challenges in these systems is how do you decide where the data goes? And there are sort of a number of ways that you could do this if you just sort of come at it from first principles. If the application wants to know where to store an object, it could sort of, in the traditional mindset, you would have some metadata server or some index that says object foo is stored on server 12, and you'd go look up which server to go to, and then you go talk to that server. That doesn't scale very well when you start going to hundreds thousands, tens of thousands of servers. And so sort of a better approach perhaps would be to sort of break apart the overall namespace and sort of into slices and put those on different servers. Here, an example, we take the first letter of the object and we slice it up. That actually doesn't work very well because you might have everything starting with A and it gets all skewed, and what happens when you add a new server and how do you balance things around. And so what we do in Ceph is sort of a two-stage hash-based approach. So in the first stage, we take this overall pool of 1 billion objects and we sort of hash the name of the object into a number of bins that we call placement groups. So this is a shard of the overall namespace. And then we use a special purpose algorithm called crush that maps each of those placement groups onto the set of servers that are responsible for storing it redundantly and safely. So in this example, if you look carefully, there are 2 copies of every placement group, so we're doing 2x replication. But it'll depend, as we get to later. But the key thing is that crush is a quick calculation. So there's a small amount of information that every node knows about who the nodes are and what the sort of data distribution strategy is. And then they can calculate where any particular object would be stored in the system. And everybody can agree on this, and so they can do sort of intelligent coordination about moving data around. And the other nice thing is that crush avoids failure devices. So sort of the inputs are the name of the object and the state of the cluster. And if that state changes, maybe a node is now down or has been failed, then it'll give a new answer for where that particular data should be stored. And it does that in a way that still obeys the overall constraints that I want 2 replicas on different hosts or whatever it might be in that particular situation. The other nice property with crush is that it's what we call declustered placement. So if you think about each of these placement groups being randomly mapped to a server, if you look at it from the other end and look at what's on a particular server, you might have 100 placement groups on one node. Each of those 100 placement groups is replicated on a different server. So when that particular node fails, the recovery is a whole bunch of 100 other servers copying to 100 other servers in sort of a massively parallel distributed way. And so you avoid the sort of the single disk bottleneck that you get with a RAID system or a mirrored system where one disk has to do all the recovery. Instead, we're spreading it around everywhere, and it happens in parallel and quickly. So crush is dynamic. It's a fast calculation. It's a stable mapping, so when you add new nodes to the cluster, only a small amount of data has to move around to maintain your invariance. And it's topology aware, so you can write policies that, I want 3 replicas in different racks. Maybe I want, some erasure code where they're in different hosts. Maybe I want 2 replicas in this rack and a 3rd replica in a different data center. You can sort of write these policies and it'll obey them in an efficient, generic way. And just a reminder, all of these things are sort of in the context of pools. So you have a pool is a logical collection of objects that's broken into these placement groups, and each pool can have its own distribution policy. So maybe this pool is 2x, maybe this pool is 3x on SSDs, maybe this one's going to be erasure coded, as we'll talk about in a moment. But this is sort of the volume-like concept in Rados. So I'm going to start by talking about tiered storage, now that we've sort of done the intro. Are there any questions before we sort of get into the meat of it, or should I just dive in? All right. So tiered storage. So we're going to talk about cache tiering. And before we get sort of into what Ceph does, at a high level, there's sort of 2 ways that you can deal with caching. The first way and the simplest way, and the way that people have actually done in the past, is just to, within each OSD, instead of attaching an OSD to a single disk, you have a disk and an SSD, and you do some sort of tiering within each node. So you combine an SSD and a hard drive under each OSD, and you make local decisions about what the hot data and the cold data is, and you sort of do all of that sort of locally. And the nice thing is that this can happen entirely underneath Ceph with existing tools. There's like DM cache and Bcache and flash cache and all these block devices. They're even controllers. Most of your caching RAID controllers can do some sort of SSD caching too. And so you can actually do this without Ceph being aware at all of what's going on. You just have this sort of magic block device in the system that does all these decisions. The problem with this is that you sort of have to plan ahead when you're deploying a cluster how much cache you want, and you have to sort of figure out what that ratio of SSD to disk is ahead of time. And if you change your mind and you get it wrong, you have like every single node you have to go reconfigure and add a new SSD or something like that. So it's not the most practical way, but works. So the other sort of approach is to cache on totally different devices and totally different hosts. And so the idea here is that we have racks and racks of SATA disks that are sort of the cold data, and then we have a smaller set of hosts that have like PCI attached flash and really fast processors and fast networks, and those would be the cache tier. And then we have Ceph manage the migration of data between those 2 sets of servers and make everything work. And so that's actually what we're going to talk about here. So the basic idea here is that we have an application talking to Rados. It could be RBD, it could be the Rados gateway, it could be something that's natively using our API. And we have a pool in Rados that's the cache. replicate it and we'll back it by SSDs. And then we have another pool that's larger, presumably. That's the colder data. That's the base tier that we call it. And that might be erasure coded, it might be replicated, whatever it is, and it's probably on slower hardware. So there are a few basic principles in terms of how Rados approaches this. The first is that each tier in a tiering architecture is a separate Rados pool. So it has its own, each tier is durable, meaning that when you write into the cache, it's actually replicated on multiple nodes, hopefully on different SSDs on different hosts, so that if one of them fails, it's still totally fault tolerant. And each of those tiers is going to have its own crush policy, crush rules. It says maybe this particular tier, the cache tier, is going to be 3x replicated on SSDs on these hosts, and maybe the base tier is going to be 8+4 erasure coded on these slower disks on this other set of servers. And the nice thing is that because we're doing all of this at the Rados layer, and the librados has just enough smarts to understand what's going on with the tiering, everything that's built on top is totally unaware of what's going on. So that means that the gateway, the block device, the file system, any other third-party applications that are using that API, they don't know or care what's going on. They just sort of see the magical performance benefits, which is nice. So I'm going to sort of high level how the cache actually behaves. If you have a Ceph client, in this case it's a Rados client, but it could be block or something on top. If it does a read, all those requests go to the cache tier first. And if it finds the object in the cache tier, in that cache pool, great, then it will return the result. That's a cache hit, and that's what you want. You want all your hot data to be on the flash. If it misses, it can simply proxy that read to the back end and actually do the read from there and then send the reply back. And so you get sort of the slower performance, and there's a little bit of cost because you're going through this intermediate node, but it's not too bad. You put high-end nodes generally in that cache tier. And if you're a little bit less fortunate, or maybe you decide that you've had several reads on the same object that you actually wanted to move it into the cache, then the system can decide to do a promotion, in which case it actually reads the object out of the back end in its entirety, and then it writes it into the cache tier, which means it's going to be replicated on 3 SSDs or something like that. And from that point forward, then any other subsequent reads will be a hit from the cache. So again, kind of what you would expect. And LibreOffice just crashed. Sure. Uh-huh. Uh-huh.
Is there any concept of RAM caching? Do you cache at RAM?
Yes and no. So usually there are lots of things will cache in RAM, but that's going to happen on the client side usually. And that's usually where it makes more sense. On the server side, we use the page cache for the file system that's actually storing the data, and so there'll be some caching there. But the important part is that from the user of librados' perspective, everything in Rados is durable and fault tolerant and highly available. So you don't write into memory. I mean, you could construct OSDs that are lying and actually saying that it's in different racks on a different UPSs or something. You could do that, but that's not really the goal. Perhaps. You could totally construct that with the existing tools. You would just back it by a RAM disk. Be aware that we're sort of trying to make something that's actually durable. That's the word I'm looking for. Yeah. We don't really want to lie to the users. Yeah, because that can lead to sadness later on. Right. So if we miss the cache, if we're reading from an object multiple times, then we'll sort of say, okay, this is actually a hot object. Let's move it into the cache, and we'll write it into that tier, and then subsequent reads will be fast. No, I'll talk about that in just a moment, but it's really about temperature, and that's the tricky thing to estimate. On the right side, it's similar. So if we do a write into the cache tier, if the object's already there, great, then we'll just do that mutation or update or whatever, and we'll acknowledge it. It'll stay there. We have nice fast writes on those hot objects. If we do a write and the object is a mutation, it's not creating a new object, then we need to have the old version of the object so we can modify it, and so it'll do a promotion, pull it out of the base tier into the cache. And there's also something that didn't quite make the last release, but we're going to do soon, where if you have a write into an object that is not in the cache, it could actually proxy the write to the back end. If it thinks that isn't actually a hot object yet, then we can avoid that promotion, because it can be kind of expensive to do that write into the cache. So we want to avoid moving things up and down between the cache tier and the base tier if we can. But this didn't quite make the last release. It'll come in soon. But the trick really to all this is estimating temperature. How do we know which object should be in the cache and which one should be in the base tier? And we do a couple of things to do this. The main tool in our toolbox is a Bloom filter, which is basically a sort of a space and memory efficient way to estimate the context of a very large set of objects. So it's assumed that cache tiers are really big, and we want to know what things are actually being read. We don't want to make a write when we read something. We don't want to, because that would be sort of a horrible performance thing. But we need to somehow estimate what are the things that are being read that are in the active set, so we can make sure that they stay in the cache and the other things get pushed out. So what we do is we have these in-memory Bloom filters that we do over sort of periodically over time. So every hour we have a Bloom filter that says this is the set of objects that were read or written during that period, and we persist the last, n of those, maybe 8 hours or 24 hours or something like that. And we use that metadata to capture, to estimate the temperature. So if an object appears in every one of those, and that object has been read sort of frequently over that last period of time. And we can also estimate recency. How long has it been since the last time this object has been read? And we use those two pieces of information to determine whether or not we push something out of the cache or whether we pull something in. And then there's sort of in the background then, we have to make these decisions about whether we want to flush data that's in the cache that's been modified, flush it out to the base tier, and whether we want to delete it from the cache entirely because it's become cold. So there's this flush decision, which just sort of takes the dirty object in the cache and writes to the base tier, marks it clean in the cache again. And then there's an evict that just deletes it from the cache, and then the reads will have to go fall through back to the base tier. And the thing that's actually making these decisions is called the tiering agent. So for every placement group, every shard of this or caching tiering, there's sort of a background state thread. It's not actually a separate thread, but whatever. There's this logical agent that's going through periodically and looking at the objects that are in the cache and deciding whether to keep them, whether to kick them out, whether to flush them, and so on. So you can set sort of you can set a ratio of how much data in your cache you want to be dirty. So maybe you only want 50% of the data to be dirty in the cache, so that when there is pressure to delete stuff, you can actually delete things without doing the flush. And you can also set the size that you want the cache pool to become. Maybe you have this many SSDs on this many hosts, so maybe it's 100 terabytes. And so when it sort of approaches that size, then it'll start kicking stuff out. And it does it by looking at the distribution of those temperatures and sort of kicking out the things that are the coldest with the right ratio to sort of reach the steady state that it's going for. So that's sort of a high-level view of how things work. There's sort of some gotchas and caveats. So the first thing is that obviously the cache tier needs to be faster than the base tier, or else you're not really going to win anything. So when we do all our regression testing, we actually just run it all on disk, and so it's not meant to perform, it's just meant to torture the system. But in reality, you want to use SSDs or something nice and fast for the cache and something slower, otherwise the cache doesn't actually buy you anything. The other thing is that the cache tier is a tier in and of itself, and a write into the cache needs to be durable. So the cache tier itself is replicated. And a consequence of that is that promoting and demoting things, moving it between the cache and the base tier is expensive. And so we want to avoid thrashing and moving things up and pushing them out as much as possible. So the system is going to work best when you have a workload that's highly skewed, where there's sort of a small subset of your data that's receiving the lion's share to the I/O. And then there's sort of this long tail of cold data that can sort of safely fit in the base tier and not thrash your cache. The hard part is that it's actually very hard for people to benchmark this and sort of set this up and see that it's working, because it's hard to sort of estimate what the skew in your real world workload is. And it takes a long time to warm it up. So people want to set this up and run DD and see that it's magically faster, and it's actually very hard to just like run a benchmark that that shows that it's working. I don't know, hours, days. It really depends on the size of the data set. Like you really have to have a workload that is touching all the right data with the right proportion with the relative sizes of your data set. So it's tricky. So it's a powerful tool. There are lots of workloads where it works great, where you have like all this new data gets ingested and gets used actively for 24 hours and then sort of gets colder over time. Like those types of situations, it's perfect. If you just like throw it at an OpenStack cluster and expect it to like work magic, your results will be varied depending on how skewed your workload is. So moving on to sort of the second thing. Actually, can I just check my time because it reset when I have another. It's like halfway through, I guess. When do we start? Yeah. Yeah, okay. So the second sort of piece of this puzzle is erasure coding, which is this. So traditionally, Ceph, as it was developed, supported replication, which is sort of the simplest way to make sure that your data is stored durably in the system. So you have one object of 1 megabyte, you have 3 different copies on 3 different servers, you consume 3 megabytes of space. It's very high durability, but it's a high overhead. It's a lot of extra hard drives to buy. But recovery is pretty quick. You just copy any of the other copies, and you're all good. Erasure coding, which is sort of similar to what RAIDs are doing. It's sort of calculating a little bit of extra redundancy for your object. So the storage overhead is much lower. So typically, depending on what code you choose, it might be 1.2x, it might be 1.5x, something like that. But the trade-off is that recovery is a lot more expensive. You have to do more I/O if you lose one of these sort of pieces to recover. So in this picture, we're taking like our 1 megabyte object, we might break it into 4 256K pieces, and then we'll have 2 extra 256K shards. So the total amount stored is 1.5 megabytes, which is nice when you're buying petabytes and petabytes of disk. So the question is, how does Rados manage this? So it looks similar to what we do with replication. So we still use Crush, except instead of asking Crush for 3 different OSDs to store the data on, now we ask it for, in this example, 6. 4 of them are going to store pieces of the actual data, and then those extra 2 are going to store the parity. And then each of these PGs kind of looks like this, and you have a bunch of PGs in the pool, and life is sort of the way it was before. Sort of looking at how an object gets translated into these little pieces on disk, you can imagine that if you have an object, you're essentially striping it across these 4 objects. So the 0, 1, 2, 3, these are the different stripes. Maybe it's like 4K chunks. And you stripe it across all these erasure code shards, we call them. Vertically, it's a shard, until sort of get to the end, and we sort of logically pad it out to zeros when we do our parity calculation, and we store the extra chunks over on the side. Right. So as with erasure-coded pools, we use the primary OSD for each placement group to coordinate all of this activity. So it's basically the first OSD that Crush gives us is elected the primary, and that's the one that's making sure that everybody is sort of doing the right thing. So in the read case, the client will send the read to the primary, exactly the same way it does within a replicated pool. In fact, the client requires no changes for this to work. Except the replica, or the primary, instead of having an entire copy of the object, is going to send off little messages to the other shards to gather up all the pieces it needs to satisfy that particular read. Pull them back, do the erasure code calculation, possibly if it needs to, or assemble the data, and then send the buffer back to the client for the reply. So the client literally doesn't even realize anything is different, but the primary is doing all the work. Similarly, on the right side, the client will still write to the primary OSD. It will do the erasure coding calculation to generate those additional parity blocks, send them out to the right OSDs, and then gather up the acknowledgments. And once everybody commits, it'll send the reply back to the client. So relatively straightforward. What happens if one of the nodes is down? So this is sort of the degraded state where I have 5 out of 6 OSDs active. In this case, we'll do the same steps, except we'll only write to 5 out of the 6 shards, and we'll send the reply back to the client. And then later, when that OSD comes back online, it'll do the same recovery sort of path that it would do normally to repair the situation. What happens if we have a failure while a write is in progress? This is where things get a little bit more interesting. So in this case, we have all the little pieces that are being sent off to the different shards, and say we crash halfway through. So half of them commit, 3 of them get updated to the new version, and 3 of them get left in the old version. This leaves us in this sort of awkward state where we have 3 versions that are at B and 3 versions that are at A, which if you recall with erasure codes, and in this particular example, we have 4 plus 2, so we have 6 shards, but we need any 4 of them to recover the data. In this situation, we actually have 3 copies, or 3 shards for the old version and 3 shards for the new version, so we can't actually recover the old version or the new version, which is sort of problematic. This is exactly what happens with the so-called RAID hole with controllers that don't have non-volatile memory to sort of make sure that partial stripe updates don't corrupt your data. So what do we do? That's a little tricky. So we sort of place some restrictions on the way that you're allowed to use erasure-coded pools. The general problem is that overwriting in place when you're doing these erasure code updates just doesn't work, because you might end up with half old, half new. So we can't do that. We could do logging. We log the new update, and we do sort of a 2-phase commit to sort of apply them after everyone's sort of rolled forward and so forth. We could do that. It would be a lot more complex. It would be some additional latency and extra IOs, and so we're not super happy about it. What we do instead is we just restrict the set of operations that you're allowed to do on an erasure-coded pool. So you're allowed to create objects. You can append to objects, make them bigger, as long as you're sort of stripe size aligned, and you can delete objects when you're done. And that's sort of the entirety of the things that the Rados erasure code pools allow. Yes? can you can you can make your stripe size smaller. I think the libraries that are sort of CPU optimized to do the actual calculation are less efficient when you do that, but it could be done. I think the bigger issue is that if you do a small read, like say you're reading a 4K piece or whatever, if the stripes are big, then you can just get that one piece from that one shard that has that data and return it. And with the byte type situation, you have to get all copies and do some math in order to get the result. And so it's less, yeah. But in Ceph's case, the stripe size is totally tunable, so you can sort of choose the trade-off that makes sense. That's for your workload. So the key reason why we restrict the set of operations in this way is that all of these are operations that can be rolled back. So if we create an object and we have to roll it back from B to A, we can just delete it. If it's we're appending, we can just truncate off the new data that didn't get fully committed. And if we removed it, we sort of save the old version for a while before we delete it, so we can just take the old version of the object and swap it back into place. And sort of the other bits of the object, there's some attributes that we store on objects that are still fully mutable. Those we store in the log, so we have sort of a nice safe place to put those, and they're safe. And then the key value data, which doesn't really map onto erasure code, we just don't allow for erasure coded pools. So these are really pools that are optimized for storing big objects with lots of bytes that are relatively cold. And you just sort of write them all once, they get efficiently stored, and you can read them all back however you like. So in this case then, when we have this partial failure, and we have some of these at B and some of them still at A, we can just roll back by taking the previous, in this case probably truncating the object back for the stuff that we didn't fully commit, and we're back to a fully consistent view, and life is good. So again, we're sort of maintaining this invariant that we never lose data, right? We can tolerate any combination of failures. Yes. Yes, I'll get to that in just one moment. There's a reason why this talk is about erasure coding and cache sharing all at once. Right. So you'll notice that this is a small subset of the allowed Liberatos operation. So Liberatos is this very rich API that lets you mutate objects. You can store attributes, keys, values. You can push code onto the OSDs to do some custom weird transactional object. You can do crazy stuff with Rados. The erasure coded pools take a small subset of that. But it so happens that the things that we don't support for erasure coded pools are also the things that are just based on first principles are just really inefficient for erasure codes. Like a small update, doing a 4K update in a large object with an erasure code, you have to read in the stripe, decode it, possibly make the update, and then re-encode the whole stripe, and then rewrite the whole stripe. So you would never want to do 4K small updates on something that's erasure coded because it would just be too slow. So we just say, forget it, we won't do that. And we'll focus on the things that actually you do want to use erasure codes for and which are fast. So it turns out that some applications can use these erasure coded pools directly because that's exactly what they need. So the Rados gateway, for example, which is providing these S3 object storage, the S3 API is such that you upload big objects once and then you store them, and you can't modify them once they're uploaded. You can upload a new version and that'll sort of atomically replace the old one, but you don't modify anything in place. And so for the Rados gateway, it can just store things directly in an erasure coded pool, and it just works perfectly. There are no modifications actually needed. There's a few things that we had to do to sort of make sure that the stripe size was aligned with the writes that Rados gateway was doing, but like that's it. And for applications that don't work that way, you can combine the erasure coded pools with the cache steering. And so the basic idea is that you have a replicated pool that supports everything, where all the hot data is and where all the small reads and writes are happening. And then when things get cold and you're not modifying them anymore, then you push them into the erasure coded tier, which is slower. But that happens in sort of one big write. You write out the object in its entirety, and it stays that way. So you get sort of the best of both worlds in that situation. And then the things that the erasure coded pool doesn't support, like those small writes, that means it pulls it back up to the cache tier. Or if you're storing key value data, for example, you don't push it into that tier because it just doesn't support it efficiently. So this sort of begs the question, perhaps, which erasure code actually should you be using? Which one did we choose? The way we approach this is that basically we don't care. We made a generic plugin interface that lets you plug in different modules to do different erasure coding strategies. So jerasure GS-complete is the free and open source library that is the default. It's very fast. It uses like the SSE instructions on Intel processors, and it's great. And it supports like every weird variation of Reed Solomon and whatever else that you would actually want to do. So that's good. There's also the Intel ISA library that Intel contributed. That's sort of similar. It's a subset of those codes, but it's the ones that people normally use, and they're super optimized to run on Intel processors with the new processor features. So they're like as fast as it could possibly be. It's like these guys who optimize based on each different variation of the processor, and they take a different path to make sure they're exercising it to its fullest. It turns out that erasure is actually pretty good, so the ISA one's going to be 20% faster. So it's not as big a win as you would expect because you can actually do pretty well and still be generic, but it's good. There's an LRC plugin that I'll talk about in a minute, and there's also a SCaLE plugin that came from Fujitsu that also, both of these ones trade a little bit of extra storage for more efficient recovery that I'll cover in a moment. In all cases, you can pick the K&M values, so you can do a 4 plus 2, you can do an 8 plus 3, you can do a 22 plus 7, you can do whatever parameters you want, so you can decide how it's configured and what striping size to use. And that plugin is just responsible for doing the math. The generic Ceph code takes care of moving all the data around and doing all the recovery and all that stuff. The plugin just has to say, like, generate these shards, and if I have these particular pieces available, which ones should I read in order to do the recovery? What's the most efficient path to do that? And so it's a very sort of generic framework. But sort of a key challenge in all of this is the cost of recovery. So imagine for a minute I have a 1 terabyte OSD, and it dies, right? So if it's a replicated situation, I have to read that 1 terabyte from somewhere else and repair, right? In reality, it's actually sharded into lots of placement groups, so I have a whole bunch of other 0.1 terabyte pieces that are being moved around to do that recovery. But in the aggregate, in total, I'm reading 1 terabyte of data to recover that 1 terabyte that was lost. So that's pretty good. The problem is that with erasure coding, if I lose that 1 terabyte disk, I have to read all the other shards that are sort of logically comprising the stripe, maybe 7 terabytes in order to reconstruct my 8 plus 2 code in order to rebuild that 1 terabyte. So recovery with erasure coding could be much more expensive. And at SCaLE, if you have some certain rate of failure, then this can actually be problematic. You have to be able to sustain the background level of rebuild to repair out around failed disks. So one of the ways to mitigate this is what we call a local recovery code. And this isn't sort of unique to Ceph. This is something that I think Facebook pioneered that they do in their big erasure coded Hadoopy thing, but we implemented too. And the basic idea is that you start out with, say, a 4 plus 2 code. So I have 4 data shards and 2 extra parity. And then I sort of group them into sort of subunits, and I add 1 additional parity that's sort of a local additional parity for just that subset of the blocks. So 1 and 2 gets A, 3 and 4 gets B, and X and Y gets C. And then if I have a single failure, if I lose only 1 shard, I can do just this local repair, where I only have to read 2 terabytes for my 1 terabyte loss, do a local repair, and I can recover. If I have a multi-disk failure, then I have to use the full code and I have to read the whole stripe, so it's more expensive. But in the common case where there's a single failure, I can go much faster. And the way that you set up LRC, it sort of layers on top of existing code, and you can choose whatever parameter makes sense. So maybe it's like 8 plus 3, and I group it into groups of 4, or whatever it is that makes sense for your trade-offs. But the key thing is that you store a little bit of extra data, so there's some cost. It's not for free, but you get this faster recovery as a result. So I just want to take a moment to thank all the people that contributed to erasure coding. This is one of the first sort of big features in Ceph that was contributed by people, initiated by, proposed by, and mostly developed by people that are outside of the core Ceph development team. So I was kind of excited. Loic Dackery sort of pioneered this. He was at Cloudwater originally, and he's involved with FSF France. Now he's actually part of Red Hat, so he's joined our team. But Andreas Peters at CERN worked on the plugins, and then sort of the core team helped with all the sort of integration stuff. The erasure library that we used is developed by people totally unrelated to Ceph, and they're great. Intel contributed the SCaLE plugin, and Fujitsu developed this SCaLE plugin, which is sort of similar to LRC, where you're trading storage for recovery, but it's a little bit more flexible and more efficient in the way that it lays out. It's really clever in the way that it lays out the different parity blocks and sort of figures out how to do repair in an efficient way. So that's kind of cool. So any questions on erasure coding before I sort of shift gears and talk about roadmap and where things are going? Yeah. Yeah. Unfortunately, I don't. Yeah, the question is, what's the CPU cost? Is there a factor to compare the CPU cost of replication versus erasure code? Unfortunately, there's no easy answer. It totally depends on the code that you use. So if you use a simpler code, then it's a faster computation. In fact, sort of the trivial code is just like an XOR, like a RAID, and that's super fast. And I think the wider the code is, like if you do like 20 plus 4 or something, it'll be a lot slower than if you're doing like 8 plus 2 or 4 plus 2, something like that. That depends. Yes. I think it really depends on your workload, right? It's how cold the data is. Like the colder the data is, the closer to deep freeze that you're putting it, you want to use the widest, like a really wide code because it's really space efficient. Um, but it's expensive to read and to recover, and so you only want to do that when sort of it's colder data. I think common choices tend to be like 8+2 or 8+3. I think I see a lot, because then like 8+3 you can tolerate 3 losses. Um, so that's better than erasure code. One of the nice things about erasure codes is they're more space efficient than replication, and the actual probability of data loss is way lower too. So they're actually more durable. They're just slower. Um, so you want to sort of use them with the right data. Mm-hmm. Yeah. Yeah. Then the next OSD is the primary, like crush, and then it does the same thing, right? There's nothing special about the data it's storing. It's just that it's sort of elected currently based on the current cluster state. It's the one that's responsible for coordinating reads and writes and recovery and all that stuff. The question is whether there's hotspotting with OSDs. Generally, no, because we're hashing objects, randomly spraying them across the cluster, and then sort of randomly distributing PGs, and so things are well distributed. If you have like individual objects that are like way hotter than other ones, then you can have a hotspot. And there are a few tools in Ceph to sort of mitigate that a little bit by shifting reads around without actually moving data. But that's sort of, you have to, you have to sort of get down in the weeds and tune it to make that happen. Yeah. So let me, sure. Right. So the question is, how do you migrate from a replicated pool to an erasure-coded pool? So if you have 2 petabytes already replicated, what do you do? There are a couple ways you can do that. One is if you can do it sort of above Rados. So if it's Rados Gateway, for example, then you just say all new buckets are going into the new erasure-coded pool, and maybe you sort of migrate them later. That's sort of the easiest thing. The other sort of clever way is that you can configure the tiering such that that existing replicated pool is now the cache tier, and the base tier just happens to be empty, and it's the erasure coded tier, and then the agents just go through and start pushing everything down. That's sort of the trickier way to do it, and probably what you would do in an existing environment where you want to make this change. Yeah. So a little bit about what's coming next here. So on the erasure coding side, we want to optimize the path for reads on the clients at some point. So we haven't done this yet, but usually the stuff that's in the erasure coding tier isn't actually being modified. Sending everything through the primary simplifies everything, and so that's mainly why we do it. But in most cases, you don't actually hit erase, and so you could just have the client do all the reads and then assemble the results locally. And if that fails for some reason, like there's a erasing right, then it could just fall back to the old behavior. So that would be nice. There's ARM optimizations that are going to JErasure for sort of these low power. There are these awesome devices that are going to come soon where it's a hard drive that has an ARM processor running Linux. And the Ceph OSD will actually run on your drive that's plugged into your Ethernet. You have no servers anymore. It's just disks in racks, which is pretty cool. But it needs to go fast on ARM. So that's coming. On the cache tiering side, the cache pools, we want to make better decisions about when to promote and demote because it's expensive. We want to make sure we have the right data in the cache tier. That write proxying thing that I mentioned before is coming. We also want to support different types of hardware. So we just think of SSD as faster and disk as slower. That's kind of oversimplifying things. In reality, you even have different kinds of flash. So some flash is sort of the cheap flash that is slow for writes and not as durable. And you have other flash that's really expensive. But often those two kinds of flash are equally fast for read, but it's just really the write profile that's different. So maybe you only want to pull things into the cache when they're written, but reads you like always proxy. And so supporting all these sort of different types of tiers and making sure that we're making the right decisions based on that is interesting. And then on sort of stepping back from cache tier specifically and just the overall tiering infrastructure, one of the key things we want to do is the ability to say, enable more complicated tiering architectures by saying that, this object should be stored here, but I'm just going to have sort of a redirect that says, actually, I put it over there in this other object in this other pool. Maybe it's like a really cold pool that's like the 22 plus 8 erasure coded tier or something like that. Or maybe it's like off on a tape library, or maybe it's off on some other cloud storage servers or something like that, and integrate that into the system because that'll enable lots of other interesting architectures. There's lots of other ongoing work in the Ceph ecosystem. I'm sort of focusing on the Rados features right now, but one of the biggest things that's going on is just people are really interested in performance and making Ceph go fast, particularly on flash. the names here are like SanDisk and Intel and Samsung and Mellanox. Like all these people, like they sell flash and they want a sort of a scalable data center thing that's going to go super fast. So lots of great community contribution there. And we're also looking at new OSD backends. So today the OSD sits on top of a file system and a journal on top of a disk. It's sort of an old approach and implementation, and so we're sort of taking that internal abstract API that we implement and building a totally new backend that's like, what's a smarter way to lay out objects on a disk? And how can we leverage key value stores to their sort of use them what they're good for and use the POSIX file system for what it's good for and just be faster. So lots of work going on there. On the network layer, there's RDMA support that just went in, came from Mellanox. That's pretty exciting. And there's also a new network implementation that's event-driven instead of thread-driven. That's also seems to be faster, but they're sort of in the process of being stabilized. On the Ceph file system side, lots of work going on there, sort of more than ever, in fact. Mostly around consistency checking and FS check tools. Sort of the main blocker to people deploying CephFS in large production environments is knowing that there's a corruption or something they can go recover their data. And so that's sort of the laser focus issue that the development team is spending their time on. And then there's other cool stuff coming. On the Rados block device, we want to have like asynchronous mirroring to another data center so that if you crash, you get a point-in-time consistent backup that you can fail over to that's on the other side of the country without sort of killing performance, that sort of stuff. I just have a list of URLs here. I'm going to post these slides later. So places you can go. All the developers are on email and IRC, and you can follow us on Twitter, all that good stuff. So that's it. Thank you very much. And happy to answer any questions. Yes.
So you mentioned there was some advancements in, I guess, or interest with faster media.
Mm-hmm.
But also you hinted a little bit at the interconnect stuff, right?
Yeah.
Because Mellanox has more interconnect
yeah.
media.
Right.
So can you talk more about that, or InfiniBand, or?
Yep. So I mean, at one level, they're just totally independent problems. We want to push stuff over the network as quickly as possible, and so it's great for that. On the other hand, once you have the super fast network, if the storage is still slow, you need to actually make it fast too. And then there are also some sort of more exciting things where there's a lot of work in the non-volatile memory space. And sort of the ideal world is that the data comes screaming off the network, it gets written directly into non-volatile memory, and then Ceph is just sort of passing pointers around and never actually copying the data. And eventually we say, oh, this is stored, it's stored in this object, and we just sort of point to the memory. So we literally like never copy the data, and we get good performance. So that's sort of the end goal. But there are lots of things that need to happen to get there.
RAM kind of by design is just another tier, right?
It could be, right. So it could be a tier within an OSD. So maybe you have a combination of NVRAM and flash and disks. It could be that you have just pure NVRAM nodes. So you're using like R cache tiering, and so you have all the hot data sitting in RAM and the cold data sitting, on disk or on flash or something like that. Yes. Compare with Lustre, is that what you said? Yes. Okay. So the question is, have we seen Ceph in HPC environments, and how do we compare it to Lustre? Yes. Ceph was designed for HPC. That was where all the underlying research came from. In practice, we haven't seen a lot of large deployments. Like the big supercomputing centers still focus on Lustre and not Ceph. But we'd love to go there, right? And in fact, HPC is a good use case for Ceph, for CephFS in its sort of earlier stages too, because it tends to be scratch data, and so that's like they're hammering on it, and they don't care necessarily if they don't have a file system repair tool because they're used to Lustre breaking anyway. Sorry, maybe not, depending on how long they've been using it. Yeah. But I think it's also a little bit challenging because Lustre has been like relentlessly optimized for 10 years. And there's a lot of all these exotic networks, and there's a lot of work that's gone into that. And so it's hard for us to sort of, when it's not actually our focus, because we're mostly looking at sort of the other 99% of the market, to focus on those use cases. Yeah. And I think that the key thing, right. So I think the key thing is that Lustre is designed for specialized hardware. Not sort of commodity pieces, and it's not designed to to handle fault tolerance in the software. It does it in hardware. So you have like a Lustre file system that's built out of these highly reliable DDN arrays, and they stripe across it. Whereas Ceph is trying to do all of that in software, so you can run it on like Dell boxes or Supermicro or whatever Quanta, whatever you get, right? Yes. Mm-hmm. Mm-hmm. Lower level. So that's right. So the question is there value in an API that's not HTTP based on the Rails gateway? And I think the answer is that that's what Librados is. So we have this lower level object API that's used internally by everything. And if you write your application to that, then great. It's going to go super fast. You cut out all these middlemen. You have this very rich storage semantic. You can push code to the objects. You can run it on the OSDs. You can do structured data. You can do atomic transactions. You can do all this crazy stuff. And so if you're building like the next Flickr type thing, build it directly on Rados. And it's usually not that different. Like usually people build it on top of a file system and they're just using these mangled file names anyway, and they don't need all the POSIXy stuff. It's usually not that much work to just store it directly using the lower level API. It's harder depending on how old your application is and how many sort of words it's grown. But
So you said with Librados you can run code on the OSD? Like
yes.
say with an image you wanted to do
Yes.
command forms or something dynamically?
Yep.
And have it run close to where the storage is actually.
Right. Yeah. So the Librados feature is called a class, and the basic idea is that if you think of object-oriented programming as having the data and the code, and you can think of OSDs as giving you the basic set of methods like read and write and delete and set attribute, and classes let you write your new methods. So maybe it's an image class that lets you generate a thumbnail and return it. Maybe it like filters out red eye. Maybe it does a rotate, and the client will just send the command that calls that class like an RPC, and that will happen like in the I/O pipeline on the OSD, sort of below all the machinery that does all the networking and rebalancing stuff, and just above all of the transaction stuff. So the result might be to modify the image, and it'll generate a transaction that's then replicated in the sort of same safe way that everything else happens. So it's sort of nicely sandwiched between those two layers. So if you use it, then it's pretty powerful. Yes. Yes. So yes, RDMA went into Hammer in the form of the XIO messenger. It's not sort of built into the release packages. It's not fully supported yet, but the basic functionality is there. And so Mellanox and this company Cohort FS, who are actively developing, are working on it more. But it's at a state basically where it's good for benchmarking and testing, and they're still sort of sorting out a lot of the issues. And they're working very closely with the Mellanox team who built this XIO messaging library to have all the features that they need to make this work. So it's great. It's an open source project, this XIO stuff, that is sponsored by Mellanox, but it's actually not specific at all to Mellanox hardware. So it'll work on any RDMA verbs stuff that you have. But it's pretty cool. It's very fast. Yes. Yeah, so the question is, how do people monitor? There are several things. There's like Nagios plugins and stuff like that for basic health. There's a tool called Calamari that's sort of an overlay management interface that we built on top. And there's a GUI that's built on top of that call it Romana. That initially was sort of the enterprise offering from Inktank. Now it's totally open source now that Inktank got bought by Red Hat. So you can go and it'll give you sort of a high-level view. Since then, there are also several other GUI monitoring projects that have cropped up. There's like Metro Ceph, and there's one from Cisco. There are several others. So there are a few options to choose from. But we're trying to coalesce development around at least the Calamari API for doing that management and reporting statistics and doing the graphing and stuff like that, and then build a GUI on top of that. Yes. Yes and no. I think that if I know what you're referring to, the question is about T10 deployment. You're talking about doing an extra parity information on each block on the disk. So it's certainly valuable if we can get checksums from all the way from the client all the way to the disk and back again and verified. That's the end goal, and that'll still be important for replication certainly. Erasure coding, it's a little bit less important because you're going to validate it when you do the erasure to code, and we have some extra checksums that we can do. The challenge is mostly around the APIs and plumbing it through the POSIX file system that we're sitting on and so forth. So we do background scrubbing and we check checksums then. But what we don't do is if you have eventually, what most people are deploying an XFS, if you write an object, it goes onto the disk. If it gets flip a bit and you do a read, it's going to read from the primary. It's not going to verify that checksum all the way back up, all the way out. And there's a lot of extra bookkeeping we would have to do to accomplish that. And things like T10 will help. But we're sort of trying to find the best interfaces and ways to do that. Yes?
What about addressing the issue geographically streaming data, for instance, fitting into like specific news videos or documentaries or
Mm-hmm.
giving reviews, or in the case of multi-master write situations
Yeah.
where you now distributed and there's multiple masters to locate them.
Yeah. So the question is how we deal with georeplication and moving data to the right geography to serve requests. That's something that the Rados gateway builds on top of Rados. So you would have different Ceph clusters, or maybe it's the same cluster but different pools that are in different geo regions. And then the Rados gateways are federated, and so they'll replicate. And right now they do active passive, like master-slave. We're working on doing master-master, so you can write to any region and it'll figure it out. But that's one place for using the RESTful object API where that would work. If you're doing something like block, because there's a sort of the strong consistency requirement, we can't do the sort of eventual consistency tricks that you can do with object storage. And so that's very hard to do. There are people who deploy Ceph across multiple data centers, like they're European and the opposite ends of the country are only a couple milliseconds. And so they just span a single Ceph cluster across those data centers, and it works. You get pretty good latency, and it's fine. For larger distances, that doesn't work. You have to do some sort of asynchronous replication. So one we're working on in the block layer to have an asynchronous mirroring thing. So you'll have a point-in-time consistent copy of your disk image, but it'll be, seconds or minutes out of date. And if you have a data center failure, you can roll back and have something that'll immediately mount and boot up. And we'd like to do the same thing in Rados at sort of the lowest level, so we capture all these use cases. But it's a very tricky problem because the goal is point-in-time consistency, and a point in time is difficult to define when you have thousands of nodes and even like relativity and all. It's like just it's challenging, and so that's sort of what we're working through in order to how to provide that. So you can build it on top with as long as the APIs that you're using are sort of appropriate for what you're trying to accomplish. Yeah. Yeah.
So for erasure encoding, what are good types of workloads? Like you mentioned, like the standard, I guess, OpenStack,
Block,
I guess.
maybe
block.
not. Yeah.
There's like the VM, I guess, part block stuff might not work so well.
It's
would streaming media work better, or streaming media with sort of a static archive where you do reads, or can you do,
So it's anytime you have so the question is what workloads are good for REC. So it's anytime you have like just really cold data, then you can do this cache tiering erasure code trick and you can push it down. That just happens to not be very true of like clouds with disk images.
Yeah.
Sometimes it will be, but usually not. Object storage is usually a good fit. So anytime people are storing stuff in S3, they're sort of self-selecting for big immutable data. And so that can go straight to EC. That tends to work pretty well. Streaming media is a good match. The sort of the trick with erasure coding is when you are doing a read, it's striped over more devices, where it's replicated, it's sort of you can read from the first one. But if you just make the objects, say you're doing 8 plus 3, if you make the objects 8 times bigger, so that effectively you're still reading from 4 megs here, 4 megs here. If you just sort of align the striping such that it's actually equivalent to erasure to what you get with replication, then it tends to work pretty well. Any kind of cold archival stuff. Yeah. All right. Thank you very much. Oh, one more. Yeah. Encryption. Yes and no. So encryption could mean a million different things depending on where you encrypt and who holds the keys. The encryption that we do support is at-rest encryption, and it's layered on the disk just below the file system that Ceph is consuming. So there's basically tooling that will automatically configure decrypt, and it'll handle all the startup and shutdown and stuff. The gap right there is that the key management currently is very simple. It's just stored on a different disk on the host in Etsy Ceph keys. And so the next key is to sort of step is to put that in on some key server or on the monitor or something to be a little bit more intelligent. But it does give you that key property where if you yank one disk, um, it's gibberish, and you can also throw the disk away and not worry about compromising data, which is important. Yep. Yes. Right. So the question is about sort of write back from the client and also different client platforms. So we actually have pretty broad support for different clients today. Like there's even a Ceph file system thing that works on Windows that will mount, and you can do iSCSI, and there's lots of sort of porting efforts underway. I think that's actually orthogonal to the question of whether it's safe to cache things on the client and then write them back. And it mostly is a question of what you want durable to mean, right? If you want to tell your application that you wrote it and it's safe, but it's only stored in local disk, if that's okay for you, then that makes sense. Currently, nothing that's sort of within the Ceph realm is doing that right now because we don't want to confuse the situation. But there are lots of use cases where that does make sense. And so there's one of the things that we might do with RBD, for example, is allow for a write-back cache on the client side that maybe is shared between two hosts, so that another one can replay it later. And that gives you, for lots of use cases, that's totally sufficient durability for whatever it is that you're doing. Or even having a write-back cache that's local, and just make it so that if you crash and you lose it, what was written to the cluster is still point-in-time crash consistent, and so you'll lose some of your recent writes, but it'll still be mountable. That would also be pretty useful. So, all right, I think we're probably out of time, but thank you very much. I'm around afterwards.